All right, these are notes 10b. We're going to be looking at functions involving e, and we're going to look at logs properties. All right, so first of all, remember e, the natural base e. So it's an irrational number. It's defined as the following. As n approaches positive infinity, this pattern, all right, is going to approach our value of e, which is about 2.7. So we're going to be simplifying some expressions involving e today. So we treat e just like it was a variable, like it was an x. So the properties of exponents are going to apply to e also. And we want to leave our problems in terms of e. We don't want to substitute in the approximation 2.7. All right, so let's simplify the following expression. So I'm going to give myself fraction bar set up here. All right, so I got 1/2. So my 2 is going to go in the denominator. I see e to the negative 3 power. So that means to take the reciprocal. So this is going to be e to the third. All right, now this expression, a power to a power. So everything in the parentheses gets squared. Those 3 squared becomes 9. E to the 3 times 2 is 6 power. All right, we want to simplify this as much as possible. So 9/2 is not going to simplify. We can leave that alone. But we have e to the 6 over e to the third. Remember, we subtract our exponents. And since it's the larger exponents in the numerator, our value is going to stay in the numerator. So our final answer is 9 e to the third over 2. All right, here's a couple more examples. All right, so look at your problem. What are we going to deal with first? Hopefully you saw that negative 2 as an exponent, so we're going to flip this whole thing. So I'm going to make this 2e over e to the fourth squared. All right, inside my parentheses, remember this is e to the first, I can simplify inside my parentheses. So I'm going to have 2 over e to the third all squared. Now finally square everything in my parentheses. So 2 squared is 4, and e to the third squared is e to the 6th. So there's my final answer. So you want to get rid of parentheses, get rid of negative exponents. All right, let's look at C. A little more complicated expression here. All right, first of all, I see square root, so I want to rewrite that as a rational exponent with 1/2. All right, so I'm not going to do anything to my numerator yet. I'm going to leave that alone. Let's work on the denominator. Well, I know the square root of 9 is 3, and this is going to be e to the 4x to the 1/2 power. So I changed my square root, my radical, to a rational exponent of 1/2. Okay, I can simplify that denominator a little bit more before I deal with that 3 on the outside. So I'm going to leave my numerator alone again. All right, I got 3. All right, I'm going to multiply my exponents. 4x times 1/2 is 2x. So this becomes e to the 2x, all to the third power. All right, now notice I have the same bases. I can, even though I have a variable in my exponent, I can still subtract those exponents. So this is going to become e to the 5x minus 2 minus 2x all over 3 to the third power. All I did was subtract those exponents. All right, clean up here. So I'm going to get e, combined like terms, 3x minus 2 all over 3, and I still haven't cubed it yet. So my final answer here. All right, I'm going to distribute this 3 on that binomial. So I get e, 3 times 3x is 9x, 3 times negative 2 is negative 6, all over 3 to the third, which is 27. So there's my final answer. So all we're doing is applying those properties of exponents. So like I said, we treat e as a base. All right, let's look at some properties of logarithms that you need to memorize. So often in equations or expressions, we need to change our logs to other forms to be able to work with them. So this is how these properties are going to help. Alright, notice that our variables b, m, and n must be positive numbers such that b does not equal 1. Alright, the product property. Now recall that logs are another way of writing exponents. So the same property of exponents apply to logs. So what that means, and the way to remember this, let's look at PEMDAS. So parentheses, exponent, multiplication, division, adding, subtracting. Alright, so here notice that we're dealing with multiplication here. So multiplication is going to turn into addition. So I can rewrite this expression as log base b of m plus log base b of n. Those are equivalent expressions. And later on in the video, if you're interested in the proof of this, I included the proofs as part of the video that you can look at. So that's the product property. So those are equivalent. If we evaluate both of those, we'll get the same answer. All right, quotient property. All right, so what do you think? So we're dividing. So what do you think division is going to turn into what? Well, let's look back at our PEMDAS. Division turns into subtraction. So we're going to rewrite this as log base b of m minus log base b of n. So multiplication turns into addition, division turns into subtraction. And we have an equivalent log statement. And then the power property. All right, so we're at a power. So what do you think its power is going to turn into? Well, if we look back at PEMDAS, power is going to turn an exponent. I was thinking P for power, but that's P for parentheses. Let's try that again. All right, our exponent is going to turn into multiplication. So we're going to rewrite this as n times log base b of m. So like I said, think of the same properties of exponents, and since logs are exponents, those same properties are going to apply. Now all of these also work for natural log, ln, natural log. And like I said, if you're interested in the proof, it'll be later on in the video. Alright, let's see how we're going to do with this. So we're going to practice these first so we're ready to use them when we need them. So we say we're going to use the properties and simplify if you can. Okay, so we're going to expand these and try to simplify them. Alright, so notice that now here what we have is multiplication. 4 times x. We're going to break that apart. So we're going to try to simplify this. So multiplication turns into addition. So we can rewrite this as log base 2 of 4 plus log base 2 of x. So sometimes your directions are going to say expand. That's what we did here. We expanded this. Okay, that's another way you might be asked to. So expand it. Use the properties to break apart. Now hopefully you recognize that this, look out for your numbers when you have all numbers for your base and numbers for that m value. We can simplify this. Remember what this means. It's asking you 2 to what power is equal to 4. So I'm hoping you're going to say 2. So this expression simplifies to 2 plus log base 2 of x. And we want to leave it like that. We can't put it back as multiplication because that 2 has lost its log. So that's our final answer. Okay, so but like I said, be careful. Watch out for the ones with numbers like this because those can be simplified again. Not always, but a lot of times they can. So watch out for those. All right, let's look at another example. We want to expand this. So you look at it, what property am I going to use? I see division, so division turns into subtraction. So this is the quotient property. All right, so we're going to break it apart as log base 2 of m minus log base 2 of 7. All right, now look at these numbers here. Can I simplify this? 2 to what power gives you 7? Well, nothing. Doesn't work. So there's our final answer. Can't do anything else to that one. All right, here we have, notice we have an exponent, 3. All right, so exponents turn into multiplication. So we're going to rewrite this as 3 log base 2 of g. All right. And let's say it's variables, that's a g, so we can't simplify it anymore. All right, so just some easy ones with the applying the properties. Let's step it up a notch. Let's make them a little bit more difficult. All right, we got natural log here. Here again, our natural log is we treat them the same way. Same properties here work for natural log. All right, so we're asked to expand this. So look at what we've got. I do have to do a couple of steps here. I see division. I know division is going to turn into subtraction. All right, down here in my new denominator, I've got multiplication. I've got 2 times x squared. That's going to turn into addition. But I also have a power. So that's going to turn into multiplication in front of that 2x. All right, so let's break it apart. So I'm going to have natural log of 1 minus natural log of 2x squared. All right, let's work on breaking down that natural log of 2x squared. All right, so I'm going to break this down into natural log of 1 minus now this entire quantity. Natural log of 2 plus the natural log of x squared. All right, I'm not allowed that power. All right, we don't want any multiplication, any division, or any raising to a power with a log. That's how we know we're done with expanding, when we get rid of those 3 operations. All right, so I got natural log of 1 minus natural log of 2. Exponent becomes multiplication, so I'm going to get 2 natural log of x. All right, let's clean it up as much as I can. All right, watch out for this, because this one is one that's, like I said, you got to know to simplify that. Remember, that implied base there is e. So you're asking yourself, e to what power is equal to 1? So that's going to simplify to 0. And that's a common. Natural log of 1 is something you're going to keep seeing in your math career. So recognize it. So natural log of 1 is going to simplify to 0. All right, let's distribute that negative. So natural log of 2 minus 2 natural log of x. Well, simply since we don't need to keep that 0 because that's not changing our answer any. So our final answer is this. All right. All right, let's look at this one. All right, I see division. I know that's going to come subtraction. So let's take care of that first. So natural log 6 xy squared minus natural log 6. All right, instead of the square root of z, I'm going to write this as z to the 1/2 power. I need a rational exponent to be able to simplify these things. All right, what else we got here? All right, so I'm looking at this expression now. I want to break that apart. So I know that's multiplication is going to become addition. So log base 6 of x plus log base 6 of y squared. All right, now let's look at this. Power of 1/2 is going to become multiplication. So it's going to be minus 1/2 log base 6 of z. All right, are you done? Well, hopefully you said no, because we still got that y squared. We're not done expanding until we get rid of all multiplication, division, and exponents. So let's see, log base 6 of x plus 2 log base 6 of y minus 1/2 log base 6 of z. All right, do we have any numbers we can simplify? No, we got variables in the place of where our m should be, so that's the best that we can do. We've expanded it and simplified it as much as we can. Took a short problem and made it long. That's what expanding is. All right, since we've expanded, let's go backwards and let's use those properties to condense it. All right, so we want to write that we're putting our multiplication, our division, and our powers back in. Okay, so as you go through this, so they're going to all of them have to have the same base. All right, what is this implied base here? There's no base written. What's the implied base? Hopefully you said 10. Okay, so let's look at what we've got. We've got 3 plus 1/2 log x. All right, so addition is going to turn back into multiplication. I also see this 1/2, so multiplication is going to turn back into an exponent. So this is going to become 3 times x to the 1/2 power. All right, I see the minus there. Minus is division. So this is going to be divided by the 5, not log 5, because we don't have, when you condense it, you only want to have one log, or one natural log. All right, we're not going to leave that 1/2 as an exponent. We're going to change it back to a square root. So this is our final answer. Log base 10, 3 of 3 square root of x over 5. So there's your final answer. People tend to catch on to this pretty easy. All right, another expanding with natural log. All right, look at what we've got here. I see addition, that's going to turn into multiplication. I see that 2 multiplied, so that's going to turn into an exponent. And I see minus, so that's going to turn into division. So I got natural log 3 x squared over y. All right. Now let me take a moment. I know this is not on your notes, but look if I change the order of this thing around. If I made it look like this. All right. Anything that's subtraction is still going to be division. Anything that, no matter the order, anything that's addition is going to be multiplication. So these two expressions will give us the same answer, because this is going to be log 3 over y, because of that minus. This plus turns into multiplication, so this is still going to be times x squared. That x squared is still going to stay in the numerator. Where if we had something like natural log 3 minus natural log y minus natural log x, that would simplify to natural log 3. Since they're both minus, they'd both be in the denominator. Because you're going to see some of those in your practice. So I want to make sure that I talked about that a little bit. Okay, last property we have to learn for these notes. It's called change of base. If a, b, and c are positive numbers with b can equal to 1 and c cannot equal to 1, then the following expressions are true. If I want to evaluate log base c of a, I can go log base c of a divided by log base b of c. All right, as long as this is the same base, and typically it's going to be 10 because that's a common log and that's what all calculators are able to calculate, then we get an equivalent expression. The reason you had to have change of base, now with our new calculators and with the Inspires that we have, we're allowed to change the bases. In older calculators, the only log they could compute were base 10. So you had to have a way of changing some base that wasn't base 10 into base 10. But it's still around now. So like I said, we might, you might see this in your calculus or your math analysis class, so we're going to cover it here too. It's kind of one of those theorems that we really don't need anymore because the calculators have gotten better. All right, what's also true, if I wanted to evaluate log base c of a, I can go natural log of a divided by natural log of c. Because remember, natural log has the same base of e. All right, so in particular, so like I said, we're going to have base 10. So we're going to go log a divided by log c. And it evaluates that expression. And here again, if you're interested in the proof, I have it attached to the end of my video here. So another way of doing this is natural log a divided by natural log c. It'll give you equivalent expressions. So like I said, this is kind of a holdover theorem from the past because the calculators weren't able to handle change of base before. Alright, so they're asking you to use the change of base formula to evaluate the logarithm. So we can rewrite this as log base 10 of 26 divided log base 10 of 16. Remember, the 10 is implied. Or we can go natural log 26 over natural log of 16. And then you would just put that in your calculator and get a decimal approximation, 1.175 from your calculator. And we'll talk about this in class, the calculator commands. All right, one more. All right, you try it. Rewrite it and using change of base. All right, so you had a choice. You could have written log 13 over log 5, or you could have gone log 13 over log 5. Put that in the calculator, and that equals to approximately 1.593. All right, change of base formula. So learn it, like I said, in case we have to use it somewhere else. You might need to use it simplifying a derivative or something in the future. So it might come into play. It may not, but you've been taught change of base. All right, here are those proofs I promised you. All right, so please pause your video if you want to look at them in more detail. So this is the proof of the product property. All right, so you can prove that and look, or pause and look at it. Here's the proof of the quotient property. Here's the proof of the power property. And finally, here's the proof of change of base. So like I said, if you want to know the why they work, not just that they work, but why, here's your whys. All right, see you in class.